Yeah, so we are doing quite a bit, and we have done the adjoint operator. So if you look at adjoint operator, and we have done the derivations on the adjoint operator, which is inner product value B equals to inner product 2 L star B, and when U and V are the vectors. U and V are the vectors. We have also defined eigenvalues, eigenvectors in class, and we have seen the characteristic equation, which is determinant of A minus lambda I equals to 0, and that actually shows that when we have eigenvalue problem, say A U equals to lambda U, and which will give you A minus lambda U equals to 0, and you can think about say A prime matrix 2 vector equal to 0, and this is, and you can see that it's like an Ax equal to 0 system, and since determinant of A prime or A minus lambda I equals to 0, so one can say that the solution of U is not singular and it belongs to the null space. So that shows that solution belongs to null space. And the thing is that what's the dimension of null space? The thing is that the dimension of null space in general one for the distinct eigenvalues. So first we will discuss about the symmetric matrix. Symmetric matrix where A equals to A transpose. I am talking about the real matrix, real symmetric. But the complex matrix is called as it is A bar transpose, and it is A star. Okay, it is also called as Hermitian matrix. Okay, so what I wanted to focus here that for a symmetric matrix, when we have the distinct eigenvalues, definitely you get distinct eigenvectors. And in all the textbooks, generally if you look at, they have distinct eigenvalues, and getting eigenvectors are very, very straightforward. Even without knowing null space, we can find eigenvectors. That's why we never thought about this critical issue of the null space. The situation becomes cumbersome when you have a repeated eigenvalue. When you have repeated eigenvalue. When you have repeated eigenvalue, situation becomes cumbersome because the symmetric matrix I am going to discuss next, the symmetric matrix even with a repeated eigenvalue, it is possible to have distinct eigenvectors. Distinct eigenvectors means with the eigenvalues, for example, the repeated, say 2, 2, say 3, we will get two different eigenvectors. We will get two different eigenvectors. And they are also the distinct eigenvectors. There are two different eigenvectors, and they are also distinct eigenvectors. The question is, if you now look at your textbook, that your textbook cannot discuss how to get two different eigenvectors for the same eigenvalue, because they need to talk about the null space, and they didn't introduce. That's what situation will become cumbersome when you have repeated eigenvalue. And thing is that the rule wise I will be discussing more and more, and see that in all possible ways it is possible to prove that in symmetric matrix eigenvectors are orthogonal, and they are the best basis vectors I will be discussing next. So no matter if the eigenvalues are repeated or not, you will get always orthogonal eigenvectors. No matters eigenvalues are repeated or not, you will get always orthogonal eigenvectors. Okay, so the thing is that when the two eigenvectors are orthogonal, for example, this 2 and 2, you get two different eigenvectors. Based on the principle, these both eigenvectors will be orthogonal. And the point is, when you have repeated eigenvalues, that means how many times repeat, that is the dimension of null space. That means dimension of null space is what? How many unknowns you can select independently. Okay? And number of bases, which will be number of eigenvectors. So if I say there are two degrees, definitely you can say my dimension of null space is 2 and there are 2 bases, you can actually get for the null space. Similarly, if you have 3 eigenvalues, you can get 3 different basis vectors and which are individual the eigenvectors and they have to be perpendicular. So we can see that for this kind of system, one interesting thing is that the solution not only belongs to null space, but for the symmetric matrix, null space solutions are orthogonal, which is the first time we have understood. Earlier we could not find this, but here we will find that the solution belongs to null space and the solution for the symmetric matrix that on each of the null space solutions are orthogonal. So, is clear? Yes or no? Is clear? Okay. See the argument. Why I am approaching the argument? These are all like practical way to visualize. You cannot find any of the books, even not even textbook. Even I have seen your textbook which is prescribed where null space concept even is not there. That will not be that concept. So this concept is very important. Not only we are getting null space, but we have seen the first time the basis. We always talk about the basis. Basis are really independent point. But here the null space basis the first time feature of actually orthogonal, and because of the symmetric matrix, and because we will be trying to prove that the eigenvectors would be perpendicular to each other. So now will be what I discussed last in the class. I took the 3x3 matrix. Okay. So now I will be using the application of adjoint theorem. I will be using application of adjoint theorem. Okay. So I am saying my operator A equals to L star. That means I have A matrix is A transpose for real matrix or real matrix for real matrix. Okay. And now the two things I would like to prove here. First is lambdas are real. Number two, eigenvectors corresponding to distinct eigenvalues are orthogonal. Eigenvectors corresponding to distinct eigenvalues are orthogonal. So these two things. So now, I was talking so much things. I was mentioning about this. So, as I said that in this course, we don't accept anything other than we demand for proof. So we have to go for the proof of the statement. I already get the statement. Eigenvectors are orthogonal. And what for? For the symmetric matrix. How to prove that? So we have said adjoint theorem. We have said the adjoint theorem, and for the adjoint theorem it is AU, for the eigenvalue problem is AU equal to lambda U, and essentially we talked about AU equals to. That's my eigenvalue. Okay, my first proof, lambdas are real. That means one interesting thing we have found out, for the real symmetric matrix, eigenvalues have to be real. It cannot be imagined. The real symmetric matrix, eigenvalues have to be real. How to prove it? How to start it? From the adjoint theorem? Apply adjoint theorem. You have adjoint theorem is what? Inner product. LUP most usual study. So here, how do you do that? What is that?
Taking the inner product.
So what is the first step? First step is what? Inner product. Inner product. Any hands please? Any hands you can volunteer? Inner
product U comma A.
No, inner. See, our formula is inner product LUP equals to LU star B. You go with the formula. What inner product you are going to take? What inner product you are going to take? Yes, I am seeing here a lot of pausing, but I want a complete answer, but I just wait to have, otherwise just keep going. I want some answer, complete answer, because there is no point to pause. Yes, ma'am. B is not here, no? For this problem, there is no V. For this problem, what are the vectors available? You just see that? What are the vectors? Look at the board. You look at the board, what are the vectors available? Yeah, so tell me what's the inner product? Yes, that's good. LU equals to inner, okay. You are saying lambda U, which is by the property. Then right hand side of the thing is U N star, which is U. And we have seen that last class that the transpose and the same matrix have the same eigenvalues that we have already proved. So with that property, one can write it is lambda U, right? So N star, so it is nothing but lambda bar UU from the property. Now we know that LUU equals to UL star. So that means lambda UU equals to lambda bar UU. That means that lambda minus lambda bar UU equals to 0. Am I correct? U is the length of a vector, the square of the length of the vectors. It cannot be 0. Okay, unless U is 0. U cannot be 0. Why it cannot be 0? Because eigenvectors cannot be 0. So this cannot be 0. So lambda minus lambda bar must be 0. And lambda equals to lambda bar. That means lambda has to be here. So that confirms lambdas are here. That confirms lambdas are here. Okay. Next part. So now we have established that eigenvalues are real. That is very, very interesting. The eigenvalues are real. So now we have to see that now we are going to establish the proof for the distinct eigenvalues. We are going to establish the proof for distinct eigenvalues. So write down distinct eigenvalues. Okay? Write down distinct eigenvalues. So what actually happens? We have two different eigenvalues, lambda A and lambda M. Okay? Eigenvector for this is U, eigenvector is V. U and V. So equation is for this process LU equals to lambda and U, and for this LV equals to lambda and V. Alright? For this is lambda and V. Alright? Okay. How to start it? We are seeing so many vectors actually there. Remember that what we have to prove? To prove what? Can you tell me what we have to prove? Yes. No. Inner product of UV equals to 0. Eigenvectors, not the product. Understood? Eigenvectors. Eigenvectors, that's a statement of the proof. You see the English of the statement. Because eigenvectors have to work on. That's up to prove. You have to prove it. You don't have to prove it. So, how to start from the adjoint theorem? How to start from the adjoint theorem? Who can volunteer? How to start the adjoint theorem? How to start the adjoint theorem? Anybody can start volunteering? How to start with adjoint theorem? Rasuda, any idea? You see the adjoint theorem. Of course, LU will not give you any help because your objective is not to prove. That means you need to do both the vectors at the same time. Yeah, that's it. Because you see the objective. That's how we prove. What is the statement? Okay? And what is that? Lambda N U V, which is lambda N U V. Right? Right hand side. U L star V, which is U lambda M V. Am I correct? Which is also equals to lambda M U V because we have found that eigenvalues are here. So it cannot be lambda M bar. Okay? So now what we can see here, LU V, we know that U L star V, inner product, and you get lambda N U V equals to lambda in UV, and that will give lambda in minus lambda in inner product UV equals to 0, and lambda in not equals to lambda in and inner product UV equals to 0, and that shows the eigenvectors are orthogonal. Is that clear to all of you? That shows eigenvectors are orthogonal. Yeah? So, there is a proof if the eigenvalues are repeated. For example, if lambda in and lambda n both are same, there is a proof. This is not the same with the proof. And in that case, how to prove even inner product UV equal to 0? That is out of the syllabus. There are a lot of difficult proof. I don't want to get a difficult proof, but you will see that in examples. I will give the examples, and there you will see that they belong to the null space basis those eigenvectors. So that has to be proved to the null space concept. Okay. So in this derivation, null space concept has to be there, and from there we can actually prove that they are orthogonal or perpendicular. Okay. So we would like to take examples on that and see that how it can be verified. So I will be talking about the distinct eigenvalues and pick up on 3 by 3 matrix. We just write down the statement of the problem. Show that the eigenvectors of matrix A, show that the eigenvectors of matrix A are orthogonal to each other. So that the eigenvectors of matrix A are orthogonal to each other. Matrix A, which is 3, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 3. You can see that this matrix is symmetric matrix. This matrix is symmetric matrix. And first job is to find the eigenvalues. And the eigenvalues, the characteristic equation is determinant A minus lambda I equals to 0, and which will give you the equation. Can you tell me the equation? Can you tell me the equation? Characteristic equation. So we have to put here minus lambda, keep minus lambda, and keep minus lambda. Okay. So if you do that, what will you get? You get a polynomial, right? You get a polynomial. You get a polynomial. Did you get the answer? Yeah, then why are you looking at here? Any answer from your side? Any answers? What are the lambda values? Lambda equals to 1, 3 and 4. So you can see the distinct eigenvalues here. The eigenvalues are different here, right? The eigenvalues are different, right? 1, 3 and 4. Okay? So we have to find out the eigenvectors. We will find out the eigenvectors. And you will see that for this type of problem, we will see that all these cases, you want to establish here, all these cases, dimension of null space should be 1. Dimension of null space should be 1. Let's look at that one. So first we take lambda equals to 1. So lambda 1 equals to 1, and we have AU1, lambda 1, U1. U1 is the first eigenvector. U1 is the first eigenvector. Okay? So we have A minus lambda 1 I U1 equals to 0. So can you fill in the blanks? U1 1, U1 2, and U1 3. Okay? What is the matrix? What is the matrix? First row? 2 minus 1, 0. Next.
Minus 1,
Minus 1.
1 minus
1 minus 1 last row.
0 minus 0.
Okay. Next step, you know that we will do echelon form, right? That's why we have solved the problem. X equals to 0. In that case, you can get number of independent algebraic equations. The echelon form, you know, it has to have at least one row 0, right? That means what? That means determinant has to be 0. Determinant is not 0 means you get trivial solution, and trivial solution is not the case here because eigenvectors cannot be trivial. So matrix A has to have determinant 0. In that case, rank is less than the order of the matrix, and in that case, at least one row has to be 0 in the row echelon format. Is that not a clear problem? Okay. So next step is what? The echelon format. This is already 0, but this is not 0. So this has to be 0. So R2 equals to R2 plus 2 R2, no, not 2 R2. Half R2. Many people are saying many things. What is that? Half R2 say? R2 plus half R2. Yes, that's the rule. You don't forget the rule. If you forget it, it is a problem. You are following the same rule. And that's the way the systematic procedure of the rule, right? You understood why? So it is quite clear. So it is 2 minus 1, 0. 0, 0.5 minus 1, 0 minus 1, 2, which is U11, U21, U31, which is 0, 0, 0. Next step. So what will we get next? R3 matrix. Yes, one matrix. Yes. R31, R31, R33, which is R3 plus 2 R21, not R2, 2 R21. Please don't forget that one. Okay. So it is 2 minus 1, 0, 0, 0.5 minus 1, 0, 0, 0, which is U11, U21 and U31, which is 0 vector. So now we can see that the number of independent rows in the row echelon form is 2. Rank of the matrix is 2, which is less than the order of the matrix, and that also shows determinant equal to 0. So now from this we can easily see the dimension of null space is equals to 1. Why? Because we have got 2 independent algebraic equations. There are 3 variables and 1 variable you can select independently, and therefore the dimension of null space equals to 1. Okay? So what actually happens? So we can write down dimension of null space equals to 1. And with that, how will you get your equations? Your equations are, so 2u11 minus u21 equals to 0, and we have u21 is 0.5 minus u31 equals to 0. So we can assume u31 equals to alpha. If we assume u21 equals to alpha, so u21 is 2 alpha, and u11 is alpha. So your identity is alpha 1, 2, 1. Alpha is, and alpha is any arbitrary constant except 0. So you can put alpha equals 1 conveniently, and you can get eigenvector 1 to 1. As I mentioned that this type of solution, when a equals to a prime u equals to 0, this type of solutions are non-trivial, but they are not unique solution. And in that case, you can see eigenvectors are not unique because we can put any value of alpha and you can get any multiplication of the vector. But what this eigenvector means? This eigenvector means, if you look at in a coordinate geometry, this is x, this is y, and this is z. So if you see, I am going x direction 1, y direction I am going 2, and z direction I am going 1. So this is your eigenvector. What I am saying. Now if you put alpha equals to 2,
you are actually going along this line. So your eigenvector, the direction, so that's why I'm saying eigenvector talks of the direction. So eigenvector is direction. So direction will not change, magnitude will change, doesn't matter. This is my unique basis. This is my unique basis. Right? So direction will not change. Only the magnitude changes. So eigenvector, of course, they are not unique, as you see from the A prime q1 equal to 0, but they represent unique direction. They represent unique direction. Although eigenvectors are non-unique, they represent the unique direction. Understand? Yes? So you got the eigenvector. Next one. So what will be the next eigenvector? Any quick solution from your side? I won't do it, I just want to have the answer. I want to have the answer from you. U2 equals to U1 you got U2 is equals to what? I am talking about the corresponding eigenvalues lambda 2 equal to 3. What 3? How much is the eigenvector? Yes, anybody got it? This is not correct. What you got? 0 should not be there. First component should not be there. 0. What is that? Any other answer? 2 said 1 0 minus 1. One zero minus 1. And U3? And U3? If it is minus 1, there should be plus 1 minus 1. Remember that. Similarly, if it is minus 1, it should be 2. Because remember that we have some alpha here. Or else, we can have alpha equal to minus 1. Alpha could be any number except 0. Remember that. Alpha could be any number except 0. Alpha, if alpha is minus 1, it is minus 1, it is plus 1. If alpha is minus 1, it is minus 1, 1, minus 1. So these are the eigenvalues can change. So these numbers, the sign can actually flip with the magnitude the same. This magnitude this may have to be same. You can see sign can flip by this. Okay. So if you give the answer, my eigenvector is minus 1, 1, minus 1. I say, well, yes, this is correct. But not minus 1, minus 1, minus 1. That's what. Will be correct. This is correct. But thing is, I got this from the first time, from this process. You can get that way also, no problem. Okay, but remember that always when you pick up arbitrary constant, always pick up U3 1 equals to 1. It is better because we are trying to solve first this one, 0 U1 U2 and U3, and U3 the last will go from here. It is better. In that case, calculation is easier. You can always come from here also, no problem. But if you go from here, your manipulation is much easier. That's why I always get these numbers. Okay, now if you look at inner product, how much they are? 0. Similarly, U1 U3 is 0 and U3 are 0. But these eigenvectors are not orthogonal. Not orthogonal. They are orthogonal. Why not orthogonal? The length is not unique. So it is possible to take E1, E2 and E3. It is possible to get E1, E2 and E3. Can you please tell me what are E1, E2 and E3? What are E1, E2 and E3? E1 is the first unit vector around E1. First unit vector. Unit vector, remember that. Length has to be unique. Length has to be unique. Yes, no. Any hand please? Your answer is not correct. Yes? No, don't give any decimal. Any root you are getting? 1 by root 6. 1 by root 6. 1 by root root 6. 1 by root 6. Then 1 to 1. Next is 1 by root 2. 1 0 minus 1. And last one is 1 by root 3. 1 minus 1. 1. So now if you look at where we can draw these eigenvectors. Next job is to draw the eigenvectors. Remember that we have something called geometric bases which are along the coordinate axis. Which are on the coordinate axis. So along this 1 0 0, along this 0 1 0, along this 0 0. E1 vector, if you see, it is 1 by root 6. Root 6 is how much? It will be roughly 2 point something. Okay. So it is roughly around 0.5. Double is here, and then something here. So this is my first eigenvector. Okay, E1. Second eigenvector, it is 1 by root 2, is roughly 1.414, right? And then it is, you can see that it is slightly less than 1. So it is here, and then this direction 0, and then minus 1 I will put along this. So something like this. This is my E1 vector, this is the E2 vector. And the E3 vector is along this, and then along this negative, and along this somewhere. Am I correct? My drawing is not that good. Okay. So these three are perpendicular. This axis is also perpendicular. But my question is now, I am claiming that these three eigenvectors, they are orthogonal, they are also unit vectors. Why they are the good basis vectors compared to these basis vectors, what I was claiming last week. So these eigenvectors, they are orthogonal, they are also unit vectors. These are also unit vectors. I am saying that I have given on problem, remember that Ax equals to B, how to solve without solving. So in that case, what we have to do? X, you can express the linear combination of basis vectors. Okay? And those basis vectors could be this or could be this. I am saying, I am claiming that these vectors, these basis vectors, are the better basis vectors than this. See, that's not the application of eigenvectors. If my good basis vectors are these, then why do this much of drama of eigenvectors? I don't have to do this much of drama, right? So I can directly work with this and finish it off. Since my claim is they are the good basis vectors for solving X equals to B. Why and how? That is the open question again. Now you know the properties. You think about it and tell me in the next class why they could be the good basis vectors. Let's look at the next problem. Okay. So whenever you have the eigenvectors, you have the graph paper, you can plot it out, or you can do it in MATLAB and see how the eigenvectors look like. And see the beauty of the eigenvector, they are orthogonal, they are different than this axis. And you can see that this is like a rotation of this axis. If you rotate, for some rotation, this coordinate axis will fall on this tree. Okay? So that means we can see that eigenvectors can be also obtained by appropriate rotation of the coordinate axis for the symmetric matrix. So many things I am talking and you are not writing. These are the things not ready in the books. You are missing so much things. That's what I am saying. So many things I am talking. You are not writing. Fine, I don't care also. But you will lose the point. So many things I am talking. Okay? Because these things are not there in your textbook. As I said, there is no appropriate textbook for this course. Okay, so I think I have given enough meat on the symmetric matrix. It is the right time to go to the non-symmetric matrix. So we now start with the non-symmetric matrix. So let's start with non-symmetric matrix. The eigenvector u bar, please write down here, the eigenvector u I bar of a real matrix A double bar, the eigenvector u I bar of a real matrix A double bar corresponding to lambda I is orthogonal to the complex conjugate of every eigenvector. The complex conjugate of every eigenvector, we write this as V bar J of A transpose corresponding to the eigenvalue lambda J distinct from lambda I. I will repeat once again. The eigenvector Ui of real matrix A matrix corresponding to lambda I is orthogonal to the complex conjugate of every eigenvector Vj of A transpose corresponding to an eigenvalue lambda J distinct from lambda I. Could you copy or shall I repeat once again? The eigenvector Ui of real matrix A corresponding to lambda I is orthogonal to the complex conjugate of every eigenvector V bar J, as I wrote here, of A transpose corresponding to an eigenvalue lambda J distinct from lambda R. I think you copy it, right? Okay. So what does it mean? So it says that when a matrix is non-symmetric, for distinct, I am assuming that my cells are distinct, I am having distinct eigenvalues. I am assuming that I am having distinct eigenvalues. For the distinct eigenvalues, it is possible to have distinct eigenvectors. The question now is, all these distinct eigenvectors are they orthogonal? Answer is not. So for non-symmetric matrix, you are getting the eigenvectors. The first step, it is said that eigenvectors are not orthogonal. Eigenvectors are not orthogonal. Why? Because when you write LUV equals to U L star V, and here A is not L star. Here A is not L star. So what do you get? You get lambda UV, you get, which is lambda 1 I am talking about, and which is, what is that? L star, which is question mark, lambda prime V. Question mark. Okay, because A is not equal to L star. Okay, if A is not equal to L star, there's a problem, right? So in that case, you won't get eigenvector perpendicular, right? So how to get perpendicular relationship? Any idea? I have given the statement. How to get perpendicular statement? How to get it? They won't be perpendicular. What is the statement given actually the problem in a mathematical form? Can anybody tell us? Can anybody tell us the statement? Statement of the problem. Statement of the problem. What are the eigenvalue problems here? There are two eigenvalue problems. There are two eigenvalue problems here. One is the actual problem, another is the conjugate problem. What's the first eigenvalue problem? What's the first eigenvalue problem? If you look at the statement, it's here there. First eigenvalue problem is A, no, don't say A, into A Ui lambda I U1. Fantastic. Next, A transpose Vj equals to, these two are the problems given. These two are the problems given. And what you have to show? Inner product Ui Vj bar. That you have to show. So now you can see that even for the non-self-adjoint matrix, it is possible to get orthogonality category. Even for non-symmetric matrix, so thing is that the eigenvectors are not orthogonal to each other. They will be orthogonal to the eigenvectors in the conjugate, in the conjugate form, in the complex conjugate form. So we have the eigenvectors in the real space, in the actual space. We have the complex conjugate space for the A transpose, and then you get corresponding eigenvectors. So you will get set of eigenvectors for first matrix. This is for the A matrix eigenvector, right? And for this A transpose, we have V1 bar. These are the complex conjugate of the real eigenvectors. So what actually happens? Inner product U1 V1 equals to no. Inner product U1 U1 equal to 0 for this case. When I have U1 U2 U3, what is the inner product of U1 U1? Is it 0? So then inner product of U1 V1 bar, is it 0? But this is 0, this is 0, this is 0, this is 0, this is non-zero. This is 0, this is 0, this is 1. So this is the way the thing. So as you understood, first automatic criteria for this. Now how to prove it? Now how to prove it? How to prove it? How to prove this now? So let's start. So this is the, so we have equation number A and we have equation number B. So let's look at so what do we do? Take the complex conjugate, taking the complex conjugates of B when A is the real matrix. Where is the real matrix? So what actually happens? If you take the complex conjugate A bar transpose Vj bar, we have lambda j bar, we have Vj bar. I'm just taking simple complex conjugate. The complex, the quantity is A, the conjugate is A bar. That is the way. A complex conjugate is A bar. Similarly, you know, if you have A B, you can write A bar B bar. Simple. Very straightforward. Now, from equation A and equation C, now from equation A and equation C, what you get? Now it is your part. What you want to derive? You want to prove inner product Ui Vj bar equals to 0, right? So how to start your actual theorem? Inner product AUI and Vj bar equals to lambda I ui Vj bar lambda I. I'm just using the properties. I'm just using the properties of inner product, nothing else. Right hand side will be what? Right hand side will be what? If I want to apply adjoint theorem, what will be equal to of this? Inner product Ui A star. Okay? What is that? It is inner product LUV equals to U L star B. I am applying this one here. Okay. And
And here our inner product here U, and it is B bar. So that's why it is B bar. If you have any confusion, you can directly refer to that. Next step. Next step is what? Next step. UY. A star is nothing but transpose, which is equation number C. Equation number C will give what? Lambda J bar Bj bar. Am I correct? Which will give what? Property of inner product? Lambda J inner product Ui. Sorry, my INK sometimes going top and bottom, so be consistent. Am I correct? This lambda J bar, it goes there, it becomes lambda J because you know that is a complex conjugate of J bar is lambda J. So what will you get finally? So our equality sign is from the adjointer Ui V bar J, which is inner product Ui A bar transpose Bj, right? So from here we got lambda I Ui Bj equals lambda J Ui Bj, and we have lambda I minus lambda J Ui Bj bar, and since lambda I not equals to lambda J inner product Ui Bj bar equals to 0, right? So now we can see the very interesting point. For a non-self-adjoint matrix, for a non-symmetric matrix, it is possible to have orthogonality criteria of the eigenvectors, where the eigenvector for the original matrix will be orthogonal to the complex conjugate eigenvector of the corresponding complex conjugate system. Okay, so funda is clear. All this derivation is quite clear, right? Okay, so please write down the final conclusion of the statement. This theorem implies, so this is valid for any real matrix. So this is, you can say that this is valid for any real matrix. This is valid for any real matrix. Now you please write down, this theorem implies that the eigenvector of the matrix A, this theorem implies that the eigenvector of a matrix A corresponding to lambda I. This theorem implies that the eigenvectors of the matrix A corresponding to lambda I is orthogonal. This theorem implies that the eigenvector of a matrix A corresponding to lambda I is orthogonal to the complex conjugate of all the eigenvectors of its adjoint, which correspond to all the other eigenvalues. Let me repeat once again. This theorem implies that the eigenvector of matrix A corresponding to lambda is orthogonal to the complex conjugates of all the eigenvectors of its adjoint, which correspond to all other eigenvalues. Okay, will you write it down or shall I write it once again? This theorem implies that the eigenvector of a matrix A corresponding to lambda I is orthogonal to the complex conjugates of all the eigenvectors of its adjoint, which correspond to all the other eigenvalues. Okay. Now, lot of things actually coming up one after another. Now I claim that, see, symmetric matrix, it was very easy to prove that eigenvectors are orthogonal. Non-symmetric matrix, we have found the orthogonality criteria between not with the original eigenvectors, they are orthogonal to the complex conjugate. I have not talked now about these eigenvectors. Are they really independent? What are they actually? So this question remains unanswered. This question